In this talk, I'll talk about how to synchronize datasets with near-optimal communication and computation costs. My name is Lei Yang, and I'm a recent PhD graduate from MIT. This is a joint work with Yossi Gilad at Hebrew University and my advisor Mohammad Alizadeh. Synchronization is everywhere in distributed systems. It's essential in tools like rsync, it's there in gossip protocols in a step called anti-entropy, and it's also essential in peer-to-peer systems like blockchains. There's a nice abstraction of the synchronization problem called set reconciliation. Imagine that Alice and Bob each hold a set of fixed-length items. The items can be anything, like file system blocks, database keys, bitcoins, etc. And they want to compute the symmetric difference of their sets A delta B. In other words, the items that are exclusive to one of them. This is very useful because knowing the symmetric difference allows them to know the items they miss from each other. Notice that based on information theoretic arguments, there's a simple lower bound on the communication cost of set reconciliation, which is a sizable symmetric difference. You cannot do better than that. There are some straightforward solutions that production systems have been using. For example, Alice can just send her entire set to Bob, and Bob can then figure out the symmetric difference. But this is clearly inefficient. More optimized solutions need send hashes or Bloom filters instead of actual items, but they do not improve the communication cost asymptotically. When the sets are large, the cost is still very high. A more optimized solution is to build a tree for the items. Each internal node is the hash of its children, so we can compare two subtrees by just comparing their roots. Alice and Bob can compare the trees from root level by level to find all the different nodes. However, this involves many rounds of interaction, and you have to transmit the internal nodes, which is the logarithmic vector. There's actually a very promising solution, which is to use a data structure called a linear sketch. A sketch is a summary of a set. Under some conditions, which we'll talk about later, you can decode a sketch to get the items in the set. A linear sketch has a nice property called linearity. You can add together the sketch of set A and the sketch of set B, and the result will be the sketch of the symmetric difference A delta B. Now, Alice can just send the sketch of her set to Bob, and Bob will add that with the sketch of his set, and the result is sketch of their symmetric difference. Bob will then decode this sketch to recover the symmetric difference. I mentioned that under some conditions, you can decode a sketch to recover the items. I'll quickly explain how it works. A sketch is a collection of symbols, and each symbol is the sum of a few items. Imagine that this is the symmetric difference that Bob wants to decode, and this is the corresponding sketch, which is a bunch of symbols. Each item is randomly mapped or assigned to a few symbols. For example, here, item A is mapped to symbols 0 and 4, and so on and so forth. Each symbol is the sum of the items that are mapped to it. For example, here, symbol 0 is the sum of items A and E. To decode a sketch, we use an algorithm called peeling. We start with a symbol that is the sum of only one item, which we call a pure symbol. For example, symbol 2. It is the sum of item D itself, so we can recover item D. We can then remove D from the other symbols, and symbol 5 becomes pure, and recover item F. Remove item F, and symbol 1 becomes pure, and we can repeat the process until we can recover all the items. However, I said that you can only decode a sketch in some conditions, and the rule of thumb is that the sketch is only decodable if it has twice as many symbols as the items, and is proven mathematically. This is because the items are mapped randomly, and you might end up with conditions like this where you do not have a pure symbol to start peeling. Or you may end up with this situation that you run out of pure symbols halfway. What we see here is that traditional sketches are inflexible. There's a design capacity, which is about half the numbers of the symbols, and the capacity is fixed when the sketch is constructed. Meanwhile, we do not know how many items there are in a symmetric difference. If it turns out to be too few, we waste the capacity and incur redundant communication. If it turns out to be too many, it's likely that we cannot recover any item from the sketch. Some existing works propose online estimation protocols, but it's an extra round trip and at least tens of kilobytes of communication. And the estimates are fuzzy, which creates its own problems. Also, we have to generate sketches on the fly, which adds computation to the critical path. And the sketches are not reusable when the different size changes. What would be really nice is if we could design a universal sketch. It has infinitely many symbols, so it has infinite capacity. Meanwhile, each prefix of this infinitely long sketch is also a sketch with its capacity proportional to its length. And we can incrementally generate a longer prefix as needed. To visualize a universal sketch, imagine this synchronization protocol. Our universal sketch for A is an infinitely long sequence of symbols, and the same goes for B. Alice and Bob can generate the symbols on demand. Alice sends her symbols one by one to Bob, and Bob takes the symbols from Alice and adds to his own symbols. And by linearity, the result is the symbol for the symmetric difference A delta B. Alice keeps sending symbols until Bob gets enough symbols to decode. And this works no matter how large the symmetric difference is, because Alice can just send more symbols. We designed such a universal sketch, and it's called Rateless Invertible Bloom Lookup Tables, or Rateless IBLTs. It has all the properties we want, and it's the first realization of a universal sketch with good computation and communication efficiency. Reconciling D items takes 1.35 to 1.58 D symbols on average. Here, the coefficient depends on D. Computation cost is also low. Generating D symbols requires scanning the set log D times, and decoding D symbols takes D log D computation. Now explain how we designed rateless IBLTs. Our design space is essentially the mapping from items to symbols. For any item which is an arbitrary bit string, we need to define which symbols it should be mapped to. Then we know how the sketch looks like for any set. The key constraint here is that we want to be communication efficient. In other words, we want to make sure the peeling algorithm, which we saw as a very fragile process, can succeed with not too many symbols compared to the number of items. In particular, we want to use only a linear number of symbols. Then we'll be very close to the information theoretic lower bound. This problem seems very abstracted, so how should I approach it? We can try to constrain our design space by considering what kind of statistical properties are needed so that we can decode with very few symbols. Let's try to consider the probability that a random item is mapped to some index I. We call this the mapping probability of the ith symbol, or ρi. Given any function ρi, we can analyze the resulting random graph between the items and the symbols. I'll not dive into the math here, but in the paper, we mathematically proved that ρi must be inversely proportional to I. What we actually did was to show the converse. If ρi is larger or smaller than 1 over I asymptotically, the number of symbols m required to decode D items will be superlinear in D, which we do not like. To give you some intuitions, here's a graph when ρi is 1 over square root of I. You can see that the graph is too dense. Each symbol is mapped to too many items, and there are no pure symbols to start peeling. On the other hand, there's a graph when ρi is 1 over I squared. The graph is too sparse, and there are many empty symbols that do not map to any item, so they're kind of useless. When ρi is on the order of 1 over I, we get the right balance. The graph is sparse enough so that we keep getting pure symbols until we cover all items, and it's not too sparse, and there are not too many empty symbols. At this point, you may notice that we have showed only necessary conditions, in the sense that ρi cannot be anything other than inverse proportional in I. But what we did not show is that ρi as such will work. To prove that, we use a tool called density evolution. It's commonly used to analyze error correcting codes based on sparse graphs, such as LDPC codes. We analyze ρi in this format, and we add a coefficient alpha and shift the denominator by 1 because I starts at 0. Applying density evolution to rateless IBLT is a bit tricky because the graph is not very uniform, and we refer to the paper. But in the end, we surprisingly get a nice closed form result, which says you need eta times D symbols to decode D items when D goes to infinity. Here, eta is the communication overhead, which is the number of symbols you need on average to decode one item. and we can show eta must satisfy this closed form condition. We can plot the relationship between the coefficient alpha on the x-axis and the overhead eta on the y-axis. In our design, we choose alpha equal to 0.5, which results in eta equal to 1.35. Our theorem tells the overhead eta when the symmetric difference is infinitely large. For finite differences, we run Monte Carlo simulations. This plot shows the overhead on the y-axis as we vary the difference size on the x-axis. Notice that the overhead quickly grows. Notice that the overhead quickly converges to 1.35, which is the value predicted by the theorem. The theorem also shows the progress of decoding as Bob receives more symbols. Again, we can compare the theory and the simulations, and they align very well. Okay, now we know what the mapping probability rho I must look like. However, we still need a concrete algorithm that decides for any item x whether it should be mapped to the ith symbol. This algorithm must ensure that for a random item x, it is mapped to the ith symbol with probability rho I. Once we ensure that, our previous analysis told us that the generated symbols will be decodable. Now, how can we design such an algorithm? A very straightforward solution is to roll a dice. For each I, the dice gives us a random number uniformly distributed from 0 to 1. In practice, the dice can be a family of hash functions, and if the random number is smaller than rho I, we make the mapping. But we quickly realize that it's very inefficient. For every item, we have to roll a dice for every symbol it is potentially mapped to, so the cost is linear to the number of symbols generated instead of the number of mappings. If we want to generate m symbols, we have to do it m times for every item. On the other hand, an item is mapped to an approximately log m times. So the cost to generate one mapping is m over log m, which is super high, because many dice rolls are wasted. Instead, we can consider an equivalent problem. Imagine that item x is already mapped to the ith symbol. We now need to find the next index j that x should be mapped to. In other words, we will determine the distance between I and j, which we denote as delta. Delta is a random variable, and its distribution is determined by the current index I and the mapping probability function rho I. Very surprisingly, we can get a nice closed form approximation of the cumulative mass function of delta. For the algebra, I'll refer to the paper. The inverse of the CMF is also simple. So to sample delta, we simply sample a uniformly random number from 0 to 1 and plug it into the inverse of the CMF. Then the next index j is simply I plus delta. This is very efficient because we skip all the symbols in the middle that we do not map to. So there we have it, the full design of rateless IBLTs. To synchronize, Alice simply streams her symbols to Bob. After getting enough symbols, Bob decodes and gets A delta B. He then acknowledges and optionally sends the items that Alice is missing. This operation is very similar to the digital fountain concept and rateless codes. There are some formal connections to be made between reconciliation and the coding, which I'll not dive into, but the name rateless IBLT comes from here. There are some nice side effects. First, the symbols are universal, so Alice can reuse the symbol stream when synchronizing with multiple peers holding different sets. The symbols can be incrementally updated. If Alice inserts or removes an item, she only needs to update O log m symbols. Rateless IBLTs are very simple to implement. We did an implementation in less than 400 lines of code. It has very minimal dependency. Users just need to define how to hash and add two items. As of experiments, we did a few micro-benchmarks to compare rateless IBLTs with other solutions, and an end-to-end experiment using rateless IBLTs to synchronize clients in the Ethereum blockchain. Here I will show some results from a second experiment. We set up two Ethereum clients. One client has the most recent data, and the other client has an outdated version, which we vary its staleness. The clients then synchronize, and we measure the time and the amount of data transmitted. We compare rateless IBLTs with the production system, which we use Merkle-Trice. As we increase the staleness, the difference between the two clients becomes larger, so both schemes use more time and communication. We found that rateless IBLTs outperform the production system by at least 4x in both metrics. To recap, we showed how we designed rateless IBLTs. It's the first solution that achieves low computation cost and near optimal communication cost. There are two features. First is rateless and universal, and we saw how it eases deployment and eliminates the need for estimating the set difference size. Second is low communication and computation costs are backed by mathematical analysis. I encourage you to check out the paper for more experiments and details of the analysis. Thanks.